Today we're going to go a little bit farther with electromagnetic radiation, and what we're going to look at is something called thermal radiation. And this ends up to being a big deal in astronomy because it turns out we can measure the temperatures of objects just by studying the light coming off of them. And so thermal radiation is the topic for today. And thermal radiation, when we say radiation, we're just talking about electromagnetic radiation, light, in other words. And it happens because anything that's above absolute zero, the atoms in it will be vibrating and can give off energy. Something that does happen to be at absolute zero will still have its atoms vibrating. The idea that all motion ceases at absolute zero is a myth, actually. But something at absolute zero will still have its atoms vibrating, but they can't give off energy at that temperature. But we're not concerned with absolute zero because in astronomy, most things are well above absolute zero, although there are parts of space that are pretty cold. Still, the thermal radiation is caused because atoms vibrate, the particles in something vibrate. The higher the temperature is, the faster they vibrate, and the higher the frequency of the radiation they give off. And there are a couple of rules about radiation that were determined in they're actually mathematical or scientific laws, which are just these mathematical descriptions of what's going on again. And they were discovered in the late 1800s. One of them is called Wiens Law. And it has to do with describing the radiation that things give off. Actually, they both do. But in the 1800s, scientists developed the ability to study the light given off by an object and feed that light into photocells, things that produced electric currents or a voltage in proportion to how much light they got. And what it would let them do is make a graph of the intensity of the light, and the intensity of the light is usually measured in watts per square meter of surface of the object, and a watt is a unit of power. It's what we measure most light bulbs in even today, although now it's hard to find light bulbs that are rated by watts. Most of them talk about lumens instead. But anyway, things that might be measured in watts are I don't know, hair dryers, for instance. The amount of power they consume is roughly 1,500 watts, maybe a little more than that sometimes. So anyway, intensity is just a measure of that. And then on the horizontal axis, they would have the wavelength of the light, and I'm going to use lambda for wavelength, that weird Greek letter. And so you'd have lambda, and that's going to be measured in some unit of length, maybe meters, maybe nanometers. It depends on what you're studying. So you can adjust that to, in fact, today, I think we'll use nanometers for the wavelength. So can't read it, but nm would be what we're going to measure the wavelength in. And what they find is that things give off different amounts of light at different temperatures. But there was one thing that showed up, and that's how Wiens Law is described. By the way, the curve that I've just drawn here is the curve for something that is a very good radiator of light. It's also a very good absorber of light. And this is called a black body curve. And I'll talk about why that's the case here in a minute. Also, sometimes just called the thermal radiation curve. When scientists in the 1800s were studying this stuff, they found out that different surfaces were better at giving off light. Different surfaces were also better at absorbing light, and they were of varying degrees, but they found out that the things that were best at absorbing light were also the best things at emitting light, which is kind of a weird thing. And there was one particular type of object that turned out to be super good at absorbing light and super good at emitting light as well. And that object was something that they called a cavity. And the way they made a cavity was to make a hollow ceramic box. And so ceramic would be something made out of clay. This is kind of crazy, but make it out of clay and you fire it in a kiln and you dry it out and turn it into something ceramic. Anyway, they did this, and then in that hollow ceramic box, they drill a tiny hole. That's the cavity. Okay, now, if it was an ordinary object and it was at a particular temperature, the thermal radiation curve for it, and this is the curve for one of these perfect things where it's intensity versus wavelength. And what you do is you take the light, feed it through a prism or a diffraction grating, and study just the light at a particular wavelength, like maybe this wavelength. Feed that light into a photocell, measure the voltage of the photocell, and then track it on the thing. And you do that at another temperature and another one, and eventually you'd get enough data points to trace out this whole curve, and you'd get whatever the curve was. Ordinary objects, when they stuck them in there, not cavities, but maybe something like maybe an old stainless steel fry pan, or maybe a stove burner, or all sorts of different things. They'd have curves that would sort of act like this somewhere, but then they'd have all these dips and spikes and places where they might not be good at emitting radiation at all, and all sorts of things. Anyway, they always fell short of this perfect curve and would have all kinds of bumps and squiggles and things in the curve. But these cavities, they could take this hollow ceramic box and stick it into a kiln. Well, first of all, imagine how this tiny hole in this hollow box is going to look. If you look at that when it's just sitting there on a tabletop at room temperature, that tiny hole is going to be as black can be. And you'll never see anything darker than that. There's any light that manages to find its way into that small hole gets reflected around inside and absorbed on every reflection, and it just looks pure dark. You can do this with a cardboard box, except just imagine sealing up a cardboard box good, drilling a tiny hole in it and looking at the hole and seeing what color it was. Well, it would look black. Okay. However, with this ceramic box, they could stick it in a kiln. That's the oven that they bake ceramic goods in to get rid of all the moisture in them. And they'll bake them for a long time and do stuff like that. But if you stick this ceramic box in the kiln and maybe put it at eye level with a window on the kiln or something so you can keep watching it, you heat the kiln up. Something that happens is that the clay objects, or the objects which are going to become ceramic works of art or whatever, or plates or cups or bowls or whatever you're making, they start to glow in there. And if you looked at the thermal radiation curve from the glowing ceramics themselves, the body of it, it'd make one of these red lines like this, not such a perfect emitter. But when you study the light that's coming out of that tiny hole, it traces out the perfectly smooth curve. And here's something else that's crazy. When the objects in the kiln begin to glow, the tiny hole in the side of the box will glow brighter than anything in the kiln. And the hotter it gets, the brighter that tiny hole glows. And so that's a very interesting thing. But here's what Wien found out, or Wien, I think it was a German name. He looked where the peak of the curve happened to be, and he called the wavelengths of the peak of the curve lambda max. And he found out that lambda max ends up depending on the temperature so well that you can use it to figure out the temperature. Here's what Wiens Law looks like, or Wiens Law. I keep forgetting to pronounce it correctly. I actually took it from someone who had taken German in college, but took the class where we learned how to say this, but he never bothered to say it that way. Anyway, I'm going to write this lambda max here, and we'll be using this symbol lambda max again and again in this class, so get used to it. And remember what it means. It's the wavelength at which the thermal radiation curve for something has its highest point. So that's it. Anyway, lambda max times the temperature is equal to 0.002898 km. Now the symbols here, M refers to meters, K refers to temperature on the Kelvin scale, which I'll talk about in a minute. Now I can write this another way. I can write it in terms of nanometers, which we may actually use more, and it will look like this. 2.898, here we're using scientific notation, times 10 to the 6th Kelvin nanometers. And all I did was change the units of measurement for the wavelength from meters to nanometers, and I got the number changed by a magnitude, but that's the way it works. Okay, so that's Wiens Law, although you'll probably hear me pronounce it Wiens Law as much as Wiens, so I'll just try not to worry about that one too much. Now, let me show you something about temperature scales that we'll need for this class. You're probably familiar with the Fahrenheit scale. That's what we use in the United States. So we'll start off with things on that. Okay. The Celsius scale is what's used in most of the world. Sometimes here it's called the centigrade scale. That's an older term for it. More likely you're going to hear Celsius here. And then we're going to introduce this new temperature scale, the Kelvin scale. And we'll talk about some temperatures on here. Let's see. Water boils. And this would be water boiling at sea level. Okay. Well, on the Fahrenheit scale, that happens at about 212 degrees Fahrenheit. On the Celsius scale, it happens at 100 degrees Celsius. And I'm not going to be fussy about significant figures on here, but we'll just go with that. Room temperature. Well, it depends on the temperature of the room, I guess, but a reasonable value on the Fahrenheit scale is maybe, well, what you often hear is 72 degrees Fahrenheit. Doesn't need to be that warm, but sometimes that might be the temperature of a room. That would end up being about 22 degrees Celsius. I just did a calculation here to figure that out. So another temperature that's people commonly associated with things, water freezes. And again, this would be at sea level. It freezes at different temperatures, at different elevations and air pressures and all kinds of things. And also if you put salt in it, but we'll assume it's fresh water we're talking about. That happens at, 32 degrees on the Fahrenheit scale. So ignore that number. It happens at 0 degrees Celsius. And then you can do other things like maybe if you've monkeyed around with this, you might know something called dry ice. Actually, I shouldn't use that one because I don't know where it, what its temperature is on the Fahrenheit scale. Let's go to absolute zero instead. And again, I mentioned that absolute zero is the temperature at which things will no longer give off thermal radiation. Okay. Well, on the Celsius scale, that's minus 273 degrees Celsius. I don't know what it is on the Fahrenheit scale. It's minus 400 and some odd degrees Fahrenheit, but I don't care because if I'm doing science stuff, I am not going to be using the Fahrenheit scale. I'll use either Celsius or Kelvin. All right, but anyway, the Kelvin scale sets its zero at absolute zero. Also on the Kelvin scale, there's no degree symbol. You just stick a capital K there and call it good. Water freezes on the Kelvin scale at 273 Kelvin. Water boils on the Kelvin scale at 373 Kelvin. Now, you may notice something. The temperature of absolute zero is 273 degrees Celsius lower than the temperature at which it freezes. So is absolute zero on the Kelvin scale. It's 273 Kelvin below the temperature at which water freezes. It's 100 degrees Celsius from the freezing temperature of water to the boiling temperature. It's also 100 Kelvin. So the step size on the Kelvin scale is exactly the same as that on the Celsius scale. It's just offset. It starts counting from zero. And this is usually the temperature scale that we'll use in astronomy going forward. It's like the Celsius scale, but it's just offset by a bit. Many of the things we're going to talk about the temperatures for aren't going to make a whole lot of difference. For instance, the temperature at the core of the sun, it's about 16 million Kelvin. Well, it's about 16 million Celsius also, degrees Celsius, because 16 million, a difference of 273 isn't going to make a whole lot of difference on there, especially when we're only going after approximate temperatures. But the reason that we need that, the Kelvin scale, is because Wiens Law uses the Kelvin scale for getting the temperature. If you've taken a chemistry class, or if you do at some point, when you get to laws in chemistry that depend on temperature, it's usually the Kelvin scale that you have to worry about. Things like the ideal gas law or the van der Waals equation for a gas. Those are outside the scope of this course, but that's the way they work. So what do we have so far? We've got this hollow ceramic box. You stick it in a kiln, and it produces this nice smooth curve better than anything else that you can ever come up with. And it turns out that black objects are better at radiating energy. Turns out they're also good at absorbing energy. So you can shine all the light you want into that tiny hole in the cavity and it's not going to come back out. It doesn't reflect off the hole. So that's kind of an interesting effect. I had an odd little experiment with how good black objects and how much better they are at radiating energy away. I was camping one time at about, let's see, I think the elevation of the campground was about 6,700 feet. So it was somewhat high, but it wasn't a particularly cold stretch of weather. But I was camped there one night and I just laid my sleeping bag on a tarp outside. I was laying down watching the stars at night. Actually, I stayed up fairly late taking pictures of stars and constellations and things. But I had a black jacket that I'd been wearing while I was stargazing. And when I went to bed in my sleeping bag, I just laid the black jacket on the picnic table that was nearby. Then I got up in the morning and looked around the campground, and it was, there was grass, everything was just fine. And it wasn't below freezing. In fact, we'd left some water on the picnic table and it didn't have any ice in it, but there was frost on that black jacket. And what had happened was at night, that black jacket that was good at radiating energy away had radiated away its energy into space. It was a nice clear night, and it lost its temperature, dropped more than that of its surroundings, and it actually got cold enough that frost formed on it. So neat little thing. I got up and thought, whoa, this is cool, literally. And anyway, that's the way it worked. But this is Wiens Law. And so here's what you can use it for. For one thing, if you know the temperature of an object, you can predict the temperature or the value of its maximum wavelength, something like that. Or if you complete one of these thermal radiation curves like this, study the light coming from it, and find the wavelength at which it gives off the most light, you can use that for determining the temperature of the object. This is actually used in the types of thermometers, for instance, where you can just aim a probe at someone's forehead and measure their temperature that way, something that's becoming somewhat common nowadays. The way those work is they measure the light coming off of the person, and there's some kind of circuitry in there that determines the wavelength of the most intense part of the light and calculates the temperature on it. You can do this in a somewhat qualitative way as well. This just has to do with thermal radiation in general. If you happen to be a parent and you have children, if you just put your hand near the child's forehead, if they're at the same temperature of you, your hand will radiate as much energy to them as they radiate back to you. But if their temperature is higher than your hand, they will radiate more energy to your hand than you radiate back to them, and your hand can feel that warmth. Of course, you can touch them and actually feel it even better, but you don't even have to touch them. You can just put your hand near them and feel that higher, more radiation coming off of them, which actually has to do with another law. But this is Wiens Law, and we'll do some things here shortly where we'll take advantage of this. There's another law that has to do with thermal radiation. This one just has to do with the peak of maximum intensity, and you've got this relation between the wavelength of maximum intensity and the temperature. And so that's just one point on the curve. But there's another one that has to do with the total area under the curve. And it's this, the total area under the curve ends up equaling the total radiation, and this is over all wavelengths. So given off. By the way, given off, you'll often hear me say emitted, and that's what it means. That's what emitted means, is given off. So if you were wondering what and I may have used it already, I don't remember. Anyway, it's the total radiation given off per square meter of surface. All right, and we needed to think about that. So that kind of cross-hatched area that I just drew in here, that would be what it is. And it turns out for these black bodies or cavity radiators that the total radiation given off is equal to, let's see, I need to pick a good letter for this one. Actually, the total power radiated per square meter of surface. I don't know. I'll just call it R for the total area under the curve. Turns out it is equal to a different constant, and this one is the customary constant. It's the Stefan-Boltzmann constant. In fact, this is the Stefan-Boltzmann Law that we have here. There were two different people. I suppose I should say Stefan, because they were German. We won't do much in the way of calculations with this one, but it goes like this constant times the temperature to the fourth power. And that's the temperature in Kelvin, as is the temperature in this one. Okay, this is a very important law. Actually, both of these are very important in astronomy, because this tells us that the radiation per square meter coming off of a star goes up with the fourth power of the temperature. Okay. If you just double the temperature, so if you have some T initial, the radiation given off is going to be sigma times T initial to the fourth. If you double the temperature, so the temperature goes to 2T initial, the radiation is going to be sigma times 2T initial to the fourth. And when you have things in parentheses that are both raised to a power, you end up with 2 to the fourth. So you'd have the little sigma there, 2 to the fourth times T initial to the fourth. 2 to the fourth is 16. Well, this was what it radiated initially. If you double the temperature, it'll give off 16 times as much energy per square meter. And that going up like that is very important, because some stars have much higher surface temperatures than the sun, and they can give off much more energy. They may also have larger surface areas than the sun. Some of them might be smaller, but with a larger surface area and this Stefan-Boltzmann law, which is what we call this particular relation, we end up with stars. I just read about one this morning that gives off about 200,000 times the power output of the sun. So that's a big deal. Okay, I've got something we do that is an activity we usually do in class, but I can work our way through it here by hand, and we can kind of understand it. These are 3 different objects that are at 3 different temperatures, and I'm supposed to say which one is the hottest object here. Well, in this case, it's not very hard to tell because they're all on the same scale and same vertical scale and everything else. And I can see that the temperature or the area under this curve is way bigger than the area under this curve, which is way bigger than the area under this curve. And so this lowest curve here is the coolest object. This is the middle object temperature-wise, and this would be the hottest object temperature-wise. And I can just tell by looking at the area under the curves. It isn't always that easy, but I can also calculate the approximate temperature of these things. And what I'll do is I'll find what appears to be the peak on here. Drop a line down, and it's going to be a little tough on the lowest curve because it's hard to say where the peak is. It looks to me like the peak of the middle object or the middle line is about there. Can't say for sure, it's just kind of winging it. And this other one, let's see, maybe about here. And maybe I'm a little wrong, but I can get a bit of an estimate anyway. Sometimes if you kind of zoom in on these curves or expand the vertical axis, it'll make it a little easier to find it, but this is just what I've got to deal with. So for this one, this highest curve, lambda max, I'll drop down and read it here. Well, here's 375, here's 500. 400 might be about here. I'm going to guess this is about 460 nanometers. Now, I don't need infinite precision on this. I'm just trying to estimate what the temperature happens to be. Okay. With this middle object, lambda max is, well, let's see. Actually, it's a little more than halfway from 500 to 625. Halfway would be 562.5. So I'm going to guess maybe this one's 570 nanometers. And it's no big deal if I thought it was 566 or 568 or 575. We're just estimating the temperature here. And then this lowest one, which is actually the hardest one to tell, and you might think it should be farther to the right or the left, but I'm just going to use for that one, lambda max is 750 nanometers. Then, here's how I'll use Wiens Law for that. Wiens Law says this: lambda max times T is 2.898 times 10 to the 6th Kelvin nanometers. Or if I solve it for the temperature, I just divide both sides by lambda max, and I'll have T is equal to 2.898 times 10 to the 6th Kelvin nanometers divided by lambda max. Okay, so I'm going to call this curve here curve Roman numeral 1. I'll call the middle curve Roman numeral 2, and I'll call the lowest one Roman numeral 3. So the temperature for Roman numeral 1 will equal 2.898 times 10 to the 6th Kelvin nanometers divided by lambda max for that one was 460 nanometers. And see the nanometers on top of the fraction divided with the nanometers on the bottom, and I'll be left with Kelvin. So the temperature of that hotter object plug in the numbers to my calculator. I'll show you how I do it on here. This one I don't have, this particular model, I don't have to hit second to get the EE on there. It's just that button without anything. So 898 EE6, and the numbers input, now I just have to hit divided by 460. And I get a temperature of 6,300, which is close enough, Kelvin. Okay, well, let's do T2. That's just going to be same number on top, 2.898 times 10 to the 6th Kelvin nanometers. And on the bottom, I'll have 570 nanometers. Again, the nanometers on top of the fraction divide with the nanometers on the bottom, and I'm just left with Kelvin. And actually, I'm just going to go to my previous calculation and change that 460 into 570. And I get about, if I rounded that to the nearest 100, it would be 5,100 Kelvin. So I have that. And then the temperature of the Roman numeral 3 curve is going to be 2.898 times 10 to the 6th Kelvin nanometers divided by 750 nanometers. And I get about 3,900 Kelvin. Okay. Now, here's a few things to notice. First of all, the higher the temperature, the shorter the wavelength of the peak. Okay. As the temperature on these things went up, the peak wavelength went to the left. Now, with electromagnetic radiation, shorter wavelengths mean higher frequencies. And so if we'd been instead calculating the frequencies, which we could do, we'd find out that higher temperature corresponds to a higher maximum frequency as well. So that's one thing to notice. Also, the higher the temperature, the bigger the area under the curve. So that was fairly obvious right from the start. In fact, that's how we kind of made the guess. But all I would have had to do to rank these in order of increasing temperature would be to look at the wavelength of maximum intensity, and the shorter wavelength of maximum intensity, the higher the temperature, or vice versa. So let's write down that. The higher the temperature, the shorter the wavelength of maximum intensity. Now, you may be wondering, why in the world do we care about these things called black bodies or cavities? Turns out, stars are pretty good black bodies. They're good at absorbing light. If you shine a light down into a star, it just gradually goes deeper and deeper in the star and eventually gets absorbed by it. They're actually pretty good black bodies, pretty good at absorbing energy. So that's one reason. And then it turns out there are a lot of clouds of gas and dust out in space that are cold, and they're also pretty good black bodies. In fact, often we can't even see them except in the infrared part of the spectrum, or maybe even in the radio part of the spectrum sometimes. So those are things that we have to try to watch out for. All right, the curves that were all done on the same plot here, same vertical axis, same horizontal axis, were maybe a little too easy to figure out the temperatures of. And so I'm going to do something that is a little harder in this case. I'm going to look at some other objects here, and let's see. These ones will be called objects A, B, and C, and see what we can learn about those. Now on these ones, we don't know if they've got the same vertical axis because they're plotted on different things. And we also, if we look at the horizontal axis on these things, this one goes from 0 to 3,500. This one only goes from 0 to 1,000 in wavelengths. And then the third one goes from 0 to, well, 1,600 if you go all the way over there. But it's not the same vertical scale or same horizontal scale. At least they are all wavelengths and nanometers. But if I want to rank these on temperature-wise, I'm going to have to do something else. And I can't use the Stefan-Boltzmann Law on this one because they don't have the same vertical scale. However, I can look at their wavelengths of maximum intensity. And I'm just going to take this thing and kind of estimate where the peak is. Actually, the peak of this one looks like it's pretty close to 600 nanometers.
So with the previous curves, you could just tell without doing math which ones has a higher temperature because of how much space is underneath it. But because these ones are on different graphs, you have to do the math.
Yep. Yeah. Because that first one, they were all on the same graph, and so I knew if this one was higher, then it was the higher temperature, and if it had more area under it. But these ones, actually, this graph is shrunk compared to the other two, and so I just can't tell anything. But I can still figure out the wavelengths of maximum intensity on these, and from that, I can figure out their temperatures. So there you see, it's at about, I'll call it lambda max. For this one is just about 600 nanometers. And then if I look at this one, let's see. Yeah, the peak's about there roughly. This may actually be easier to tell. I've got a more sensible scale on this one. But it looks like here's 1,000, there's 1,500. I'm thinking it's probably about 1,350. So and you know, maybe it's 1,375, maybe it's 1,325. I'm not that worried about it, especially since this first one I looked at, object C, it's at 600 nanometers. There's no getting these two mixed up. They're far enough apart. And then I'll look at that third object I had on here, and its wavelength of maximum intensity is going to be right there. Actually, it's very close to 200 nanometers. Okay, now the thing I've got here is the higher the temperature, the shorter the wavelength of maximum intensity. That means the shorter the wavelength of maximum intensity, the higher the temperature. Which means this object B that I've got here with its lambda max at 200 nanometers is hotter than the one that had 600 nanometers. In fact, I would expect this one to be 3 times as hot as that one. And then the 600 nanometer one is hotter than the 1350 nanometer one is by a little more than a factor of 2. So let's see if those temperatures actually work out. So in every case, I'll calculate the temperature up here. T is equal to 2.898 times 10 to the 6th Kelvin nanometers. In this case, divided by 200 nanometers. And the temperature of this one, I get 14,500 Kelvin for the temperature of it. So that is pretty hot. Okay. Well, let's see. The next one, the 600 nanometer one, I sort of guessed that because its wavelength of maximum intensity was 3 times higher, maybe its temperature was only a third. So let's see. T is, again, 2.898 times 10 to the 6th Kelvin nanometers, this time divided by 600 nanometers. The nanometers divide out, and I'm just left with Kelvin. And I get 4,830 Kelvin. And how does that carry? Where did it go? That is just about a third of what that one happens to be. So, and it should be exactly a third if I actually kept the right number of significant figures on everything. But, so, less than a third. By the way, the sun would have a wavelength of maximum intensity a little bit shorter than this one, and its temperature would be a little bit higher than this. It's up 5,700 Kelvin or something like that for the surface temperature of the sun. All right, and then that last one, if we calculate its temperature, T is, try to remember the constant again, 2.898 times 10 to the 6th Kelvin nanometers divided by 1,350 nanometers. Kelvins, or the nanometers divide out, and I'm left with Kelvin. The temperature of this object is for this one, I get about 2,150 Kelvin, which is a very low temperature for a star, actually. That's not very hot at all. So a last question on these things that I sometimes ask is, let's see, except I don't know what I did with that page, somewhere here. I used Wiens Law and calculated the temperature, or Wiens Law, however you want to say it. The last thing says, see if you can estimate the color of each of the objects shown. And I'm just going to do with these last 3 objects. Well, here's the thing. The visible spectrum goes from about 400, that's 400 nanometers down here, up to about 700 nanometers. And we're going to see something kind of interesting about these graphs here. Okay, visible light fits between these two. So the portion of the light that's coming off of this object that's actually visible is just this one little corner down here. And we don't even see the vast majority of the light that's coming off of this object, or the electromagnetic radiation. It would just be invisible to our eyes. Although, if our planet happened to be in the solar system of this star, we'd experience the part of the light that is not visible. By the way, this is all going to be infrared light out here once you get past the visible little window here. And so the vast majority of the light from this star is infrared. Now, this little window down here, this is the violet end of the spectrum, the 400. This is the red end. This star gives off, or object, whatever it happens to be, gives off way more red light than anything else. And so this object would look reddish. And not too much controversy about that. Okay. Let's go on to another one of them. Object B here. Let's see, let's find the visible part of the spectrum here. This one has a nicer scale to read it off of. There's 400 nanometers. That's the violet end of the spectrum. And here's 700 nanometers. That's the red end. Now, with this one, it's a little bit tricky, but not because of what's going on here. But something we can see is that at the violet end of the spectrum, this object is giving off way more light than it is at the red end of the spectrum. Not as extreme as it was for that one we just looked at, though, where it was giving off a whole lot more red light and almost no violet light. But still, this one has kind of a better mix of colors across the visible spectrum, but still more violet than at the red end. This one would look, to our eyes, it would be a bluish white or a very bright white. And again, this is the only part of the visible spectrum that we see for this one. Most of the light given off by this star is out here to the left of the visible spectrum. This is all ultraviolet out here. So that's something. But maybe a bluish white. Sometimes you look at things like this and you just think it's a really white white. So you can look at stars at this temperature through a pair of binoculars or a telescope, and it does seem like just a white that's so bright it's got a little bit of blue to it, but hard to tell on that one. The last one that was kind of in the middle here, object C. Let's see, here's 400 nanometers down here, and try to draw a line straight up there. 700 nanometers is going to be about here. And if we look at this thing, its peak is a little ways to the right of the middle of the visible spectrum. If it's got its peak right in the middle of the visible spectrum, we perceive it as white and no bluish white to it in that case. This one, actually the 600 nanometers is kind of in the orange or amber colored. So this one I'd say would probably appear orangish white. So not so much red on this one, but kind of orangish white. Just a little ways away from being a nice balance. So there you have it. We can use the light coming from objects as a temperature gauge. This is actually used in other places besides those thermometers that they aim at people. I had a tour of, I think it's D&L Foundries that's on Wheeler Road one time. And they make things out of molten metal there. And molten metal is pretty hot. It's not the sort of thing that you can just dip a thermometer into, because if it's a glass thermometer, the glass thermometer would just melt and you wouldn't get the temperature. If it's a metal thermometer, it might melt too. But what they do instead is they have an instrument that they just aim at the top of the pot, measure the radiation, the electromagnetic radiation that's coming off of the pot of metal. And these are pots that are the size of a 55-gallon drum or bigger. And just measure the radiation coming off of it, and you can get the temperature that way. So it's taking advantage of Wiens Law, which is pretty useful in astronomy, because we don't have the freedom to go to these other stars or these clouds of gas and dust out there. The only way we can learn about them is to study the light that's coming off of them, study the electromagnetic radiation, and that can tell us their temperatures. So a useful thing. All right. Tomorrow, thermal radiation is one of the types of radiation that's given off by things. Now, thermal radiation is given off by solid objects. It can be given off by liquids, or it can be given off by gases if they're dense enough. If the gases are too rarefied, then we don't see thermal radiation in that case. We might have to use other things to learn about it. So starting tomorrow, we're going to start to learn about those other ways that light is given off and what we can learn from those other types of spectra. So we'll move on with that. Does anybody have any questions on this stuff before we stop the recording here? Not a big turnout today. So Alyssa and Maxwell, you guys are a good audience. Okay.
Thank you.
All righty. Well, we'll stop here, and tomorrow I'll move on from there. And I hope this did record. So